All right, in chapter 6, we're going to talk about the electron. If you want to follow around in your book, it's on pages 139 to 172. The electron is very, very important because it's what actually bonds. It's how we get all these compounds that make up our world. So we really want to understand what's going on with the electron and how it's theorized that this is actually happening. So there's a lot of different theories that have come because obviously you can't see an electron, and that's what we're going to take a look at today. But in order to understand how the electrons actually behave in the atoms, we really have to study how light interacts with matter, because that's something that we can see, something that we can compare it to. So how electrons are in the atom, we're going to compare that to light and how it passes through matter. Okay, so light travels in waves, but it behaves like fast-moving particles. Electromagnetic waves can be described in 4 characteristics. First, with the amplitude, which is the height of the wave. The next is wavelength, which is the distance between successive crests, or the tops of waves. And frequency tells how often it's going to oscillate. O-S-C-I-L-L-A-T-E-S. That means it goes up and down. Now, the speed of light's important because with that we can compare different ones. So the speed of light is about 2.998 times 10 to the 8th meters per second. And so what we know is that we have amplitude, wavelength is characterized by a lambda, frequency is a little v, it's the speed of light. And the speed of light equals lambda times v. So we can actually relate everything together by the speed of light. If we have a low frequency wave, this is just our origin line, it means that it's not going on very often. It's very slow. Whereas a high frequency wave is happening very frequently. Okay? Should be equal on top and bottom. Mine just isn't great. So the amplitude is actually the height of the wave, which is just from the origin to the crest. So from the middle to the top. That's your amplitude. Your wavelength is from the crest to the crest of the next one. That's your wavelength. Okay, and you'll notice that the higher the wavelength, the higher the frequency, the smaller the wavelength is. The amplitude doesn't really change depending on frequency. The height's the height, but the wavelength does. That's why we can do this relationship where the speed of light equals your wavelength times your frequency, because they are related in that way. The smaller it is, the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Okay. All right, so they're indirectly related, which is why we multiply them. Now, you've seen this electromagnetic spectrum before. It starts over here with the very low frequency, so they're not dangerous. And it goes all the way up to this high frequency, and these are the dangerous ones. And in the middle is something we call the visible light spectrum. If you've heard of this before, you may have heard it as Roy G. Biv. Roy G. Biv. These are all the colors we can see with our eyes. Red, orange, yellow, green, blue, indigo, and violet. Okay, so those are the wavelengths that we can see. They're visible. That's not all the wavelengths there are. There are radio waves and TV waves and microwaves that are happening, but we can't see them. Well, the visible spectrum is an example of what's called a continuous spectrum. All the colors kind of blend together. Whereas a line spectra, they don't. Like when you were little, maybe you drew a rainbow, you did red, orange, yellow, green, blue, and purple, and maybe if you knew enough, you put indigo in, and you put your little clouds. Okay, but that was more indicative of a line spectrum. They're distinct lines. We're going to look at these two in lab. The first one, the visible spectrum, we're going to see in the flame test, where all the flames are different colors, but they're kind of blended. And I'm going to tell you to use 2 words to describe them, because red just doesn't cover it. Maybe it's orangey red. Maybe it's more red than orange. You know, it's going to be a blend of different colors. It's not just going to be one distinct color. A line spectrum we're going to see when we do spectroscopy. And that you're actually going to need distinct lines, and every element gives off a distinct line pattern, whether it's 5 reds, 2 greens, and a blue, or 1 orange, 1 yellow, 1 violet. Okay, so every one is different. The question is, though, how is this light produced? How do we see this? And that's where we get into Niels Bohr. Niels Bohr actually is one of the founders of all the electron stuff, only because he listened to something, a lecture by Rutherford. Remember Rutherford? Right, he was the one with the gold foil experiment. So he was the one who really decided that there was a nucleus, and that nucleus was positive. But remember his issue? He couldn't tell you what was going on with the electrons. I mean, they knew they were there, but he thought they were just, on the outside somewhere. He knew what was going on in the middle, but not what was going on the outside. So Bohr was listening to his lecture and said, well, what is going on with those electrons? And that's what he started to research. Okay, he postulated or thought that in order to get spectral lines, or lines of color, the energy of the electron must be quantized or given a number. Okay, it has to be given a value in order to understand what's going on. So he labeled each energy level with a quantum number, n. So let's say this is my nucleus right here. Okay, so this first ring is n equals 1. This one is n equals 2, n equals 3, n equals 4. Okay, so he gave each level a separate number, all the way up to 7. Okay, each one got a different number. Starting near the nucleus is 1, all the way out is 7. And the lowest energy level is the one that orbits closest to the nucleus. Okay. Now, he said that that's where they normally are. And when they're normally just relaxing there, it's called the ground state. When they're just relaxing, nothing's going on. But if it absorbs the right amount of energy, it's going to jump to an excited state. Just like when you give a kid too much sugar, right? They jump to the excited state. So let's say we have an electron right here at n equals 1. We add energy to it. Whether we're doing the flame test and we add heat in the form of fire, or we're doing the spectroscopy lab and we add heat in the form of electricity. Any kind of energy we're adding, we're going to make this electron jump up 1, 2, 3, 7. I don't know, we're going to make it jump up different levels though. It's not going to stay on the same level. Every element jumps differently. That's why every element gives off a different color. Okay, so it's going to jump to a higher energy level. This right here is the excited state. It's jumping up. Now, just like kids with sugar, once it's jumped up there, it releases that energy and comes back down, right? So it has the energy, absorbs it, jumps up, and then it drops right back down to where it was before. When it drops down here, it has to release that energy. Releases energy, and we see a color of light. That's the visible part that we see. And since all the electrons in each element are different, each element has a distinct light spectrum. Okay, so whether it's a line spectrum or a flame test, it's going to be distinct. So that's why in the flame test, I can give you an unknown and say, which one is it? Because they are distinct. Same with the line spectrum. I'm not going to give you an unknown, but I could, and you could figure out what it was. Now, Albert Einstein came around in 1905, and he started looking at this stuff as well. And as you know, he was rather smart. So he actually looked at it in ways that a lot of people didn't completely understand. A lot of people didn't really understand him in general. But he found that electrons are ejected from the surface of a metal when light shines on it. So not only is it just, you add electricity to it and it gives off a light, but even when you just shine a light on it, it gives off electrons. He realized that sodium metal doesn't emit them in the presence of red light, but it does in violet. That's because of the frequency. Violet light has a very high frequency compared to red light, which is a low frequency. So the higher the frequency, the more it's affecting the sodium. And he said that the stuff that's coming off are called photons. So these light particles that are being emitted that you can see are called photons. He gave it that name. So everybody's looking at what Bohr is saying, and they're understanding it, and they're trying to basically argue with him to make up their own idea. Well, Heisenberg came around, and so did a guy named Louis de Broglie came around, and so did Heisenberg, all around the same time, and they're listening to Bohr, and they didn't really agree with him 100%. They didn't think it actually worked in orbits, okay, the way that Bohr said. They actually said that, yeah, that's where it's most likely to be found, where you're going to have a high density of electrons or right in those areas, but an electron can be anywhere it wants to be at any given time. I mean, it's a moving object. It's not like a planet. It's going to be anywhere it wants to be. So de Broglie, who's not on this outline, But de Broglie kind of compared it to a firefly, and fireflies are attracted to sugar. So if you put some sugar hanging from a string in the middle of a room, made sure all the lights were out, close all the windows, close all the doors, and release some fireflies in there, that's going to be a better indication of what an electron would do. Wherever you see that firefly light up is like an electron. So yeah, it's going to be around the sugar a lot of the time, but there's nothing stopping it from flying into the corners and going anywhere it wants to go. So that's what it's saying, that the electron is pulled in by this positive pull of the nucleus, like the sugar for the fireflies, but it's not necessarily always going to be in that orbit. It can go wherever it wants. So that's what de Broglie said, and Heisenberg here is on the same page as him. He called it an uncertainty principle. He said that you can't know the momentum position of the electron at any given time. So you can look at the firefly and see exactly where it lit up. But once it's lit up and done, you have no idea where it's gone. So yeah, you can get the position right there, but you have no idea where it's going next, the momentum. Or maybe you can figure out its path, but you don't know when it's going to actually light up. Okay, so that's what he means by position and momentum. Position is exactly where it is. Momentum is where it's going. So it's not like Bohr, where it's always around a path and you figure out where it's going to be next, or the planets, where you're going to figure out where they're going to be next. Okay, you cannot know the position and momentum at the exact same time.